So moving forward with 1D steady state conduction with no generation in radio systems, what if we have some sort of pipe that could be a pipe that's carrying oil from the point of extraction to a refinery? It could be a pipe or a tube that's in a shell and tube heat exchanger. We saw these the first week of class. But this is a much larger version of that shell and tube heat exchanger that's used in practice. Or this could be a general pipe that has some sort of fluid going inside that needs to be insulated, and it's wrapped with insulation, as you see there. So now we have a cartoon here that shows a pipe that has an inner radius, and it's wrapped with 3 different materials that could be used, for example, to insulate it. And then it has this convective heat transfer happening on the outer surface. Now, I'm not sure, you probably can't see this clearly, this resistive network for the pipe is shown here on the board, but you have it in your notes. But what we have is we have 5 different resistors in series in this problem. We have the 2 convection resistances, where we have convection on the inside of the pipe system, we have convection on the outside of the pipe system, and then we have the 3 conductive resistances in series for the 3 different materials. So, if we remember, the convection resistance is 1 over the heat transfer coefficient H times the area, and we have that same expression for the outside and inside. However, the heat transfer coefficient is different and the area is different, because for the first one, the area is based on the inner radius, R1, and for the outside one, the area is based on the outer radius, R4. And then for the 3 conductive resistances in series for the materials. Now these are the radial system conductive resistances. They're not the same as the L over Ka that we use for Cartesian coordinates and plane wall, because these have that logarithmic temperature dependence. So here we have these resistances that look like the natural log of ratios of radii over 2 pi, the thermal conductivity of the material, times the length of the cylindrical pipe. So we have that. Once we set up our resistive network, then we can move forward and set up our rate equation in terms of the total resistance of the system. So here we have the temperature, the inside of the pipe, and the temperature at the outside of the pipe, the difference between those. And then we have the total, or the equivalent resistance, here in the denominator. So that you can see this a little bit more clearly. And where we have to be careful here, or what we should note, is the choice in area usage if we decide to take this equivalent resistance and represent it as an effective heat transfer coefficient U. So this parameter U we defined previously is equal to U times A would be equal to 1 over the total resistance of that network. So this A here, this is where we need to be careful, because let's say, for example, we want to use this first area, the area defined by R1 as our A. Well, what we're going to have to do is we're going to have to extract that A out of here, because this is R here. And in order to put this in terms of U times A, we're going to have to pull an A out of this expression. So what would that look like? Well, that would, for here, look like pulling out 2 pi RL. And if you pull it out 2 pi RL over here, then we're going to end up with getting rid of this 2 pi L and then ending up with an R1 in the numerator over here. And so on and so on. That's what we have. So we can do that, and that's choosing the area inside the most inner area of the pipe as our reference area. And we can do that with any area. So any of the 5 above areas can be factored out of this denominator to define U. So if you factor out one area, you'll get one U. If you factor out another area, you'll get another U. But ultimately, you'll get the same answer. So one way to be straightforward with this, if you ever have any confusion about defining this U or A, would be just to not even deal with it. To just, each time you solve a problem like this, just write out the entire resistive network. Write the rate equation in terms of these resistors in series, and you can see everything clearly. You can see the notation, you can see the units, and it could help prevent confusion in solving the problems. So there's a case that's unique to radial conduction, and there's an example in your book, example 3.5, that goes over this. So once again, this is an example where we have some sort of pipe, and it's insulated, and we, as the engineer, want to figure out, well, how much insulation do we put on? You know, how much insulation gives us what we need? What's the cost trade-off? Well, the important parameters here are the resistance, the total resistance, and here we have, if we just have one layer of insulation, this insulation has an inner radius, Ri, at the pipe wall that has a fixed temperature, and then it has an outer radius R. So this is just showing, this relationship is showing the conductive resistance of this insulation. Then on the outer surface, you have convection occurring. And we know that the heat rate per unit length through this system, which is constant, the heat rate per unit length is constant, then that's represented as the difference between the ambient temperature and Ti, which in this case is the temperature at the inside of the pipe. So given that, we have our equivalent resistance, we know our heat rate, and we want to think about now, what does it mean to put the right amount of insulation around this pipe? Well, this is a curve that, or a plot that has 3 curves. Let's look at this first one. Well, we know if we have convection on the outside of a cylindrical surface, as the area of the cylinder increases, the outer area, the amount of convected heat will increase as well, because we have more surface area available for convection. So as this radius goes up, this resistance to convective heat transfer drops. Otherwise stated, the convective heat transfer rate increases. So that's shown here on this curve. Now we have insulation, so our goal is to keep the resistance high to trap the heat. Well, if we increase the thickness of our insulation, then as we do that, the resistance of the insulation increases logarithmically. So we have these 2 competing phenomena happening in this system. We have a system where if we increase the radius, we get more convective heat transfer off the surfaces, but if we increase the radius, then we're increasing the thickness of the insulation that we need to do its job of trapping in heat. So if you add these things together, this third curve here is the total resistance. And the neat thing is that we see here there's a minimum resistance